Mr. Nimesh Chinoy. He has been in the field of application-oriented solutions since 2003, having 4 years of experience in R&D and 13 years in sales and marketing. He has worked together on developing induction heating applications for welding for preheat and post-heat. He started manufacturing Indian welding inverters under the brand name of SigmaWeld since 2007. Mr. Nimesh will speak on applications of induction heating for pre-weld and post-weld heat treatment in various industries. So delegates, let's welcome Mr. Nimesh Chinoy.
Good afternoon, everyone, and let's dig into the applications for induction heating. A brief introduction about the company and myself. I represent Electronic Devices Worldwide Private Limited. We are into manufacturing of welding equipments, induction heaters and induction sealers, and various automation solutions. We've been around since the last 48 years, and we are largely an Indian company with exports to more than 90 countries. Today's program, we will focus more on induction heating as an alternative to gas heating and resistance heating. Its advantages and utility in many fields, especially welding and related. I'll quickly take you through basics of what is induction heating. Induction heating is a process which heats metal indirectly using magnetic fields. It's one of the most accurate, fast, repeatable, efficient, non-contact technique for heating metals other than electrically conductive metals. So all of you have been using an induction cooktop. So it's very easy to explain the concept to you using that. So for every induction cooktop you see, within the top there is a induction coil, which is represented here in number 2. And then that induction coil is actually nothing but a bunch of copper wires bound together in a particular sequence. In this case, it would be a pancake coil. And if you can see, what happens is that a lot of current goes through the coil, and during that time, it produces magnetic fields, which are these blue lines. And when you put a metal on top of it, the blue lines or the magnetic field inducts itself into the metal, producing eddy currents. Eddy currents use the carbon in the material to heat themselves up, and therefore they produce heat in the metal locally. And this is a very simple way to use waste heat, which was the magnetic field, and convert it into an efficient heating. By doing this, whatever material you have inside the vessel also gets heated indirectly. So whatever you're cooking, whether it's milk, water, tea, or Maggi, you can cook it all with induction. Induction, usually there is the concept of induction has 3 major parameters you need to be aware of: current, voltage, which give you the power, and the frequency, which determines how deep you can penetrate the heat. So if you were to do some kind of heating where you wanted all throughout the depth, you would use low frequency heating, in which case you see complete depth. If you want to heat only the surface, like certain kind of hardening jobs, you have to heat only the tip of the metal, then you would use high frequency, which would give you very shallow depth. This is a basic of what induction heating is. It is used in many applications globally. So starting from hardening, annealing, normalizing, pan bottom brazing, impact bonding, resin bonding, sintering, forging, brazing, partial heating, soldering, metal melting, gold melting, shrink fitting, pre-weld post-weld heat treatment, induction cap sealing, and many more. Induction heating has got a varied indirect heating applications, which also goes to medical fields. So all the catheter tubes that you see, which are used to give you drips, they all have an end which is tapered, and that taper is done using an induction heating application. So wide range of applications, and 3 different ways to heat today, which is largely used. One is gas-based, electric, and induction. You can see the 3 different images here. The first one represents gas-based heating. As you can guess, when you are heating, it is heating through conduction. That means the gas heats the metal surface and then it conducts the heat inward. The process is inflammable. It can catch fire, definitely. It's a fixed shape of the burner that you use, so you can heat that much area only. So you have to either increase the number of burners or change the shape of the burner when you want to change the shape of heating. When you use gas-based heating, the surroundings will also get heated up. So the operator standing around you will also feel the heat. It is non-contact, so you can rotate the job while the torch is in a fixed position, as it shows on the figure 1. It is polluting, so you have carbon emissions, which are now a major concern for all corporates as well as all of us. And the penetration is surface to core. That means the heat goes from where the touch point is inwards towards the core. Typical efficiency is 40%. That means for every 1 kilowatt of heat that you want to generate, you must use 1400 or 1600 watts of power to generate that much heat. Then you have the electrical heating, which is a nichrome based wire through which when current passes, the nichrome wire resistance tends to heat up, the wire becomes red, and therefore it conducts the heat. It is usually protected by ceramic beads, like you can see in the image here. It's flexible, you can wrap it around the shape you want. It's Again, it's a conductive method because it's get heated and then it's sharing the heat inside. And typically after winding it, you would put a cerevil on top of it so that the heat doesn't radiate into the environment and the operator doesn't feel the heat. Of course, it's non-polluting. Again, the temperature goes from surface to core. Now let's look at induction. Induction works on magnetic field as I showed you, so it need not be directly in contact with the job. So you can see the coil has the job has an insulating layer above which the coil is wound. It is non-flammable. The coil is flexible. You can wrap it in any shape you like. It generates heat very locally to where the coil or the magnetic field reaches. Of course, it's a non-contact, so you can have the job rotating. It's a non-polluting process, and the heat is evenly spread because magnetic field is inducing currents all throughout the metal. So it's inducted into the metal and you have even heating all across. What this means is the efficiency of heating in gas is only 40%. Electric can be as good as 74. Induction, the worst case you would get is an 84% transfer efficiency. So in a better case, you could go up to 90%. The advantages in the process, it's non-polluting, no flames, it's faster, consistent heating. Heat is induced directly into the metal, no conduction losses. A non-skilled person can do this. It's highly efficient and you can heat only a local area if you want. We will see a lot more in the applications as we go along. The coil doesn't get hot, so the operator can remove it on his own and start welding. So that's a larger part of the advantage because that is something which makes it easy for the operator to use. The welder can also weld while the coil is in place, so that becomes another advantage. You don't have any heat or something coming up. And economic, so it's a low power consumption, reduces the cycle time drastically, and it's excellent for preheating, and it's compulsory for few materials, for example, P91, alloy steels and others. How it works, this is just a bit, you can set a temperature, the feedback comes into the equipment manages the error and then adds the power accordingly. So as the power goes through the coil, the job gets heated and you have a sensor to give feedback. We use a inverter control loop for phase locking. So you have a very fine control over the temperature profile and you can control 1 degree as well. You can go as low as 10 degrees per hour and you can go as high as 120 degrees per hour, depending on what you want to do. A typical temperature profile for pre-weld is you heat up to 250 degrees without any ramp. You can go as fast as you can. Hold it there. Once your welding is complete, you allow it to cool down, do your radiographic tests and things like that. And then again, it goes to the post-heat cycle where you can heat up to 80 to 120 degrees per hour, depending on the thickness. Once you achieve 760 or Curie point, then you have to hold it there for 2 to 4 hours and then you have a controlled cooling up to 400 degrees and then you let it go. Now this is typical cycle showing a preheating. The lines are different thermocouples on the inside and outside. You can see how closely coupled they are. So there is no delta T between the inside and outside. And here is a 6 thermocouple graph that it looks once it's finished. And you can see they are so closely together that the temperature control is very fine. There are different modes: preheating, manual heating, interpass monitoring, post-weld heat treatment, hydrogen bakeout, and you can even customize your own site. Let's look at a few of the examples. Now, if you're doing heavy wall pressure vessels or boilers, here is a header made out of P91 material, which needs to be heated on the edges before it's welded. You need to also do post-heating, then PWHT and bakeout. These are the typical setups. You will first wind it up, preheat to 200 degrees. You can see the welder welding while the coil is in place. And then you would end up doing SAW, where the job would rotate and the head would remain fixed to finish the job. In this entire period, the coil doesn't move. The operator is very comfortable. You can see he's very close to the job while the heating is also happening and no disturbance to them. If you compare with natural gas, here is one example where a 50 thick pipe was to be preheated from the center and the welding was happening from the inside. So they were heating the torch from outside, taking it up to 200 degrees and then start welding on the ID. They used to take typically 20 minutes to achieve the temperature and they were measuring the temperature on the surface only. Here we were able to heat from the ID, thereby ensuring the temperature when you measure on the surface, the ID is surely at the temperature that you want because the welding is going to happen from the ID. We could achieve the same temperature in under 8 minutes. So you can see there is more than 50% saving in time, definitely also in cost. Same goes for even thicker vessel. This is about 150 thick, that is 50 ID, 200 OD, and a length of about 350 millimeters. This was a typical setup done by gas burner. It would take about 16 minutes before they could start welding. And here we could do it in about 10 minutes. Again, the coil going from inside and preheating. This is where you can see another example of an elbow being welded, pipe to elbow. jobs in place, two operators standing next to each other and doing the welding, absolutely comfortable, no disturbance to the weld or to the welder. When you have to do post-weld heat treatment, you need to take it up to curie point and normalize it so there are no stresses left in the metal. So during that time, you need to take the temperature to 760 degrees. Now you can see here the ring which shows you the temperature has been reached. These are 4 thermocouples giving feedback, and you can see this is the ramp rate you can preset. Right now it is in soaking period for about 100 minutes. 3 minutes have passed. The actual temperature is 753. Once the soaking, finishing, and cooling starts, it will reduce the temperature power slowly. So you have a gradual gradient up till you reach 300 degrees, and then you will get let it naturally cool in the air. If you had a very big job setup, you could use flexible C-type coil, which allows the job to rotate, and you can put it from one side and heat the job. Same thing goes for very heavy vessels. This is when you are doing it for the lip of the flange here, for the flange joint. These are almost 200 thick. These would have taken 4 hours to set up on a normal gas-based burner or a electrical resistance heating. In induction, this can do in 30 minutes. So kind of cycle time saved is very large. You can see long seam preheating of a shell happening. So this is a typical seam you have to weld. It's about 70 thick, 3 meters long. To do this, they were taking about 20 to 30 minutes to set up the resistance heating coils. And then it would take about 2 to 3 hours to achieve the temperature of 150-200 degrees. Here we have made a blanket within which the induction coil is placed. You can place the blanket on top of the job. It takes about 2 minutes to do so. Press start. In about 20-25 minutes, the temperature is achieved. Remove the blanket and start welding. You save close to 3 to 4 hours of your cycle time. That means you can produce much more faster on the shop floor. These are different examples. This is a good one where you can see preheating of a boom in the construction. You use these material handling equipments like JCB and all. They have a large boom. If the boom is not stress relieved, preheated and then stress relieved, there are good chances that under load conditions it will fail. So it needs to be preheated. Typically it was preheated with gas, but it would take a lot of time and the operator needed to be very skillful and consistent that if he did not heat, there was no way to know it was not done. Here you can see the operator is sensing the temperature. It will take under a minute for the temperature to achieve. And once it's achieved, the operator can remove it with his own hands because it's no temperature on the coil, and start the welding. And that's how easy it is to do it with induction. Time saved, the labor saved for the operator, and he would ensure that the temperature is always there before he welds. This ensures quality of welding. This is another example of doing it in a boiler industry. This is on site on many power plants. When they do erection, they have to do welding on site. Very critical places, difficult to approach. Induction makes it easier to set up. This is for cross-country pipelines. Just to show you this thermograph on your right, you can see there are 2 temperature taken within a span of 10 seconds. So it is 320, 26, and this is 320, 30. There's hardly 4 seconds difference between the temperature on the outside and inside. And you can see the temperature achieved is 143 degrees here and 133 degrees here. That means the delta T is less than 10 degrees between a 15 thick pipe on the OD and ID. And to apply this blanket, it takes about 2 minutes. Heating time is about a minute or 2. In 5 minutes, the pipe is ready to be. They have to weld kilometers of this together at cross-country pipelines. Induction heating provides a very fast and consistent service. If you look at long seams pipes being welded, again, same application, preheating for a 65 thick, we could do it within 20 minutes. And these are the calculations for the same. Another interesting application is bearing housing shrink fitting. Typically, they put the bearing into an oil bath and let it wait there for 6 hours so the temperature is stabilized. Then they have to remove the bearing housing from the oil bath and insert a bearing. So it's a 6-hour process and it's very messy. The operator has to be very skillful and careful because if he doesn't insert in due time, the bearing will get stuck. You can see here doing the same with induction. It is absolutely easy. He is heating this is the one that is being done for the stone crusher. So in the body, there is a central shaft. This shaft needs to have bearings inserted on both sides for it to be equally mounted. And otherwise, this process was done using flame, and it was a very tedious and process for the operators to do. Using induction, they've just formed the coil, left it out, and they are now patiently waiting for it to achieve its temperature. When it does achieve, then the operator is in no rush to push this forward and carry out the string fitting job. There's a flange which is going to be mounted inside, and they'll simply slide it over to achieve the desired result. I'll just fast forward this so that people can get an idea as to what it does. So there you go. The temperature on the shaft, the condition is that the base pipe should get heated, but the shaft on the ID should not get any temperature. So this is where induction plays a major role, because it's inducing material temperature directly only into the metal. So this is the shrink fitting process where they inserted a housing into the already pre-heated shaft. And this is another application of, so most of these construction equipments have a lot of welding, and which leads to distortion. At the end of distortion, you need to straighten the job back to its normal position. So there is a process called heat straightening, which at the moment is used with flames. Now induction helps you do that same thing, but with a lot more safety and ease to the operator. So here you can see they have to heat it in this V pattern to straighten the job, and with induction they just have to move it over the line and the temperature is being achieved. So it's a very, very simple and easy process. It's quick heating, increased productivity, surrounding area doesn't get heated, coil is easy and safe to handle, no fire flame due to induction heating, so it's a non-contact process. Safety and reliability of the process is very high, very repeatable. So once it's done, you can, once the trials are finalized, you can give the coil a particular shape like we saw in the case of shrink fitting, and then you can use it over and over with a lot more convenience. Thank you so much.